First off, I want to thank everyone for being here, including our speaker on such a frigid Pittsburgh morning, the one of many this week. So today we have with us, for this installment in the AI-SDM seminar series, Dr. Chris McComb, who's an associate professor in the Department of Mechanical Engineering here at Carnegie Mellon. His interests, background in human-centered design and engineering, very interested as well in the psychology-informed artificial intelligence. His lab is the Design Research Collective here at CMU, which merges perspectives in engineering, manufacturing, psychology, and computer science. And he's also the director of the Human plus AI Design Initiative. His interests lie in machine learning and human social systems for design and engineering, which offers an interesting overlap with a lot of the work being done in AI-SDM. So let's give a very warm welcome to Dr. McComb.
How's it going, everybody? So I will always happily come back to a seminar that has Dr. Pepper. This is an odd outlier, but an exciting one. So just real quick, who's from engineering in the room? Okay, School of Computer Science. Okay, Hines? Tepper? Okay.
Wait, not from CMU.
Dietrich.
Yeah, Dietrich, yeah. Round of applause for Dietrich. That's one of the things I love about AI-SDM is that it really represents sort of these interests across the university. So I come at a lot of these questions from a very engineering perspective. I think a lot about academic lineages, right? And that sort of tells us a little bit about where people are coming from. So on one side, I was co-advised for my PhD. So I had a lineage of mechanical engineers going from John Kagan, Alice Agogino, back to Doug Wild, who is one of the originators of engineering optimization. So I tend to come at this work from a very engineering optimization focus. And the other side that I aspire to is co-advisor Ken Kotofsky, who's a cognitive psychologist. So I try to adopt those perspectives in my work as well. So to sort of ground this talk, and this is probably something where I'm preaching to the choir, but AI is expected to be huge in no more than a couple of years, right? Already is. If we start to unspool economic impact that's predicted from AI across time, we see, yeah, pretty steady rise, but we're expected to see a lot of gains in GDP, right? National objective versus personal objective coming from labor productivity. What I care about in engineering, we also are seeing some adoption of AI techniques in especially engineering relevant fields and functions. So we see big penetration into technology, advanced industries, consumer goods, and surprisingly, not that much making into manufacturing. Of course, when we look on a corporate level, the last couple of years have been exciting, right? Lots of adoption, maybe for better or worse. And once we started tracking this subdivision of AI that we refer to as generative AI, we see a really steep rise there as well. And I can certainly share slides out through AI-SDM, and some people are like grabbing references, taking photos. Happy to share these. The other place that we've looked is in education. And I love this plot because it shows where we can reallocate effort to save time for educators, right? So we have student engagement and instruction, right? A lot of time, 16 hours a week. We can maybe allocate 2 of those or reclaim 2 of those through some intelligent AI support. But what's more exciting is things like preparation or administration, right? Where there's potential to reclaim instructor time on the order of 50%, right? And what that means is that we can reallocate that time towards deeply human things, right? Things like engaging with students, near to very, very near mentorship and things like that. Of course, we've already started to see AI applications changing the way that we create and design things. These are a couple of brackets that I believe have orbited the Earth and made it back down. So these are designed using some sort of a Gen AI system. I think they're overclaiming on the left a little bit. This looks a lot more like topology optimization to me. But I believe their claims a little more with this part. So a big piece of the work that my group does comes from this motivation of AI changing the way that we do engineering work. The second theme is that teams are everywhere. Teams also change the way that we do engineering work. What we know, and I probably don't need a citation for this one, but teams are common in industry, right? But we also know that more than 50% of patents have multiple inventors, right? And you could argue the degree to which patent co-authors are collaborating or not, but it's an indication that there's some degree of collaboration. We also know that more than 80% of science and engineering publications have multiple authors. So the way that we create innovation in industry, the way that we study teams, the way that we learn about teams in science and engineering is all driven by teamwork. So these are inescapable. AI is here to stay and it's getting bigger. Teams are a fundamental part of how we work as humans. So my group, the Design Research Collective, focuses on sort of three stages of work. The first stage of work is deeply understanding human designers, engineers, and problem solvers. So we do cognitive studies. We also do a good degree of simulation work to understand human systems. Second, once we have a better understanding of the humans involved, we start to build AI support to help them out. So to help them be better at what they do or better at what they want to do. And then we also look at human AI collaboration. So once we have sufficiently proactive tools, they start to look a little bit more like partners or managers in some cases. And there's this really deep bi-directional effect. So I have a smattering of different projects from my lab that I'm excited to show off. And we'll look at a couple under each of these headings. And actually, when do you want me to stop talking? Is that at quarter till or at the top of the hour?
We usually leave a little time at the end for Q&A, okay. So you go till 12:50-ish. That's usually good.
Making sure. Great. Thank you. So under the area of human designers and engineers, I sort of hinted to the idea that my lab uses a spectrum of methods. So everything from what I would call more conventional human subjects research towards computational models that allow us to simulate and make hypotheses about human behavior. So along this spectrum, I have had folks look at a variety of different topics. One of my first graduate students was looking at stress and mindfulness in the engineering design process, primarily focused on human subjects research. Mohammed, who I'll share a little bit about in a bit, focused on empathy and trying to chart the dynamics of empathy growth and change in design teams. Harshika Singh looked at peer influence within design teams, taking a lot of inspiration from influencers and social media to do that modeling work. Noriana Radwan, who I'll also speak about in detail, looked at cognitive style, which has deep implications for how we work in teams and how we do innovation. And then Aslan Nurgasimi and Sean Rizmiller are more on the computational side of things. Aslan has been looking at community resilience in the Arctic through computational models, and Sean Rizmiller was looking at set-based design. But I want to zero in on Mohammed's work on empathy and Noriana's work on cognitive style. So starting off with empathy. In design, we talk about empathy a lot, right? You want to empathize with your users and develop that deep understanding so you know their needs, right? So you have an understanding of how to help them out. And this has led to lots of amazing products. Sometimes empathy just starts to sound like a fuzzy word. This is actually something that we can measure. And one of the scales from psychology that we've used in my group is called the Interpersonal Reactivity Index. So this is a short series of questions that essentially places you on two axes, right? So the first is affective versus cognitive, right? Am I empathizing from my thoughts or from my feelings? The second is, in this empathy, and am I being self-oriented or other-oriented? So in some cases, right, we have like perspective taking, right? Imagining how another feels or thinks. This is a really productive form of empathy. On the other side, right, still cognitive, but affective and self-oriented, we have something like personal distress, right? This is where you're empathizing so deeply on such an emotional level that it's a little less productive, right? You're just feeling terrible for this person. So it's about balancing. And some of the work we've seen is actually that empathic concern and perspective taking are the two more valuable types of empathy in engineering design. How we discovered that is running a human subject study where we looked at the way that people develop and grow empathy in a first-year engineering design course. So we studied this over a 7-week project. So they started off doing basic user needs assessment, some concept generation, concept selection, and then into detailed design. Our interest here, so typically you would start building your empathy in these early stages, right? We wanted to understand how that impacts your later stages. So does that impact the quality of the ideas you come up with? Does it impact the creativity of the ideas, et cetera, et cetera? And then we also looked at patterns of concept selection. But I want to zero in on concept generation today. So first, we looked at individual level. So participants were asked to individually generate as many solution concepts as possible for the project they were working on in class. So we characterized every individual according to their empathy, right? Their strength of fantasy, personal distress, perspective taking, and empathic concern. And then we also evaluated the solutions that they came up with. So we in engineering design use consensual assessment technique from Amabile, and that allows us to do this scoring in a way that is qualitatively rigorous. So we can assign numerical values that indicate the overall creativity of the ideas, the elegance, the usefulness, and the uniqueness. So with this data set, we can start trying to make a connection between individual characteristics of empathy and the types of ideas that people are generating. So we fit a model and we got nothing. No correlations, nothing significant. Individual empathy does not predict overall creativity, does not predict usefulness, does not predict uniqueness or elegance. So this seemed weird because we have a really strong hypothesis that this should have an effect. What we didn't directly resolve here was the fact that people are working in teams. So that was our next step. We repeated this analysis, now instead looking at fantasy, personal distress, perspective taking, and empathic concern from the perspective of elevation and diversity. So we refer to elevation as the average value of those within the team, and then diversity is the range of those values within the team. So those become our new predictors, and we also look at aggregated scores for overall creativity, elegance, usefulness, and uniqueness. Some of the scoring for these relies on scoring concepts relative to one another. So that's where we introduce some nonlinearities that actually give us some significant effects at the team level. So go through this modeling effort, and when we look at team level results, there are a few hotspots that come out. Because of essentially the fact that our study was a little bit overpowered, many of these are significant from a statistical level. So I want to focus more on practical significance. So what are the ones that have a larger impact? So when it comes to personal distress, engaging in a degree of personal distress substantially decreases the usefulness of the concepts you come up with. So feeling distressed through your empathy process is directly counterproductive. And this is specifically elevation. However, we see that when we're looking at uniqueness, we actually benefit from a degree of perspective taking. So by putting ourselves into the shoes of the user from a cognitive perspective, we can actually learn pretty well how to come up with unique ideas to suit their needs. So this is an example of work that we do in a more pure human subjects research domain. Next, I want to transition into some work that we've done looking at cognitive style. And here we've embraced something called agent-based modeling as a technique of rapidly conducting computational experiments to generate hypotheses about how people might behave or perform. So in agent-based modeling, we make a one-to-one correspondence between individual humans and software artifacts. So these software objects we imbue with characteristics that we care about individuals. We can also imbue them with the ability to interact in ways that emulate human systems. So within this team of 4 individuals, some of them might be closer to others. They might have feelings of mutual affiliation or affection. And those are things that we can also start to model computationally. I like to say that good agent-based modeling usually looks like a sandwich. And this is a Pittsburgh sandwich because we have fries on it. but it's a sandwich, right? We always need to start off with some empirical slice of bread, right? It's either an observation from the real world, something we're interested in, something we picked up from the literature, right? But we always need the empirical slice of bread to start building the sandwich. Then we get to the fun part, right? We get to top it off with all of these fillings, right? We get to make modeling choices about how we want to resolve the different aspects that we care about. But good agent-based modeling really doesn't give you too much beyond hypotheses, right? So it's always essential to come back with a second slice of empirical bread to close off the sandwich. Nobody likes open-faced sandwiches. Your fries are going to fall all over the place. So here we specifically looked at something called Curtin's Adaption Innovation Inventory. So who has heard of KAI before? Okay, so this is an inventory that's about 30 questions, and it gives you 3 subscores. But the major score is this adaption innovation spectrum. It is normally distributed. For general population, the mean is at about 95. And you see we get several sigma out on the ends, and you're really going to be hard pressed to find anybody that's above a 160 or below a 32. What it means on the upper end is that these are people who we refer to as innovative. This doesn't necessarily mean we can't be innovative in a means of creativity. Here, innovative means that they like to do things differently. They like to think laterally. They like to learn the rules just enough to start breaking. On the other side of the spectrum, we have people who we refer to as adapters. So adapters are people who like to learn the rules and then work very closely within the rules, right? I think everybody can probably think about where do you fall on the spectrum. I'm an 87, so I'm right here. And what that means for all of us, we have a preferred style, right? That's what the survey gives you. But we also know that coping behavior plays a really important role in cognitive style. What that means is that with effort, you can change your displayed cognitive style for some degree of time, right? If I need to be a real lateral thinker and creative, I can do that. I'm going to get really tired, right? But I can. So we wanted to better understand how people interact in teams with respect to cognitive style. Because what we know from the literature is qualitatively, once people are about 10 points apart from each other, it's a just noticeable difference. So if you work closely with that person, you'll start to realize that they think about problems a little bit differently than you. As that gap opens up, it becomes exponentially more difficult to get things done with that person unless there's adequate coping behavior. So this has some pretty important implications for how teams work together, but there are also relationships to incremental versus radical innovation, right? Our adapters are probably more well-suited for incremental innovation, right? Really optimizing the next pen to use, 5% less plastic. But the people who are going to be creating, world-changing products tend to be our innovators. So my grad student developed an agent-based model, and this is one of my favorite titles, the KAI Agent-Based Organizational Optimization Model, or KABOOM. So this model is based on simulated annealing as a core construct. So is anybody familiar with simulated annealing? Okay, is anybody familiar with mechanical annealing? All right, good. Wrong side of campus. So simulated annealing is an optimization algorithm that's stochastic and global. So the primary measure that we care about is something called temperature. So as our algorithm has a higher temperature, it bounces around more and will search more broadly and divergently. As we progressively lower the temperature over time, the algorithm becomes more deterministic and engages in more downhill search. There's a string of research starting in about the 1980s that shows that simulated annealing is actually a good computational proxy for patterns that people follow in problem solving. So this has been really well validated on like tavern puzzles, but also some engineering design tasks like truss design as well. So in this work, we wanted to see if we could simulate the design of a race car, essentially. So this is an SAE formula car. If you're in mechanical engineering or an engineering school, this is a common student competition project. And we worked with Oregon State University, which is one of the premier teams in this competition. They worked with us to develop a systems model of the vehicle. So we have a way to predict performance of the vehicle based on a set of 60 parameters. So 60 parameters are what we tasked our agents to go ahead and design. We put together a team of 33 different agents with 11 teams, one for each subsystem of the vehicle, and 3 agents on each team. So we have a team of teams that's collaborating to do this work, and they're organized according to this Kaboom framework. Of course, we're interested in cognitive style. So the question here is, if we know a little bit about the different subsystems of the vehicle, if we know about the tasks that our team members are going to be engaging with, can we better design the team to place people with the right cognitive style in the right place at the right time? So we started looking at whether that even has an effect in a computational simulation. So we held the KEI of every sub-team constant except for one of them, and then we jiggled it, right? So we hold rear suspension non-constant, we slide that more adaptive, more innovative, and here we're doing an maximization problem, right? So we want high quality, and that means that, for instance, for rear suspension, our simulation says we should get the best performance from adapters. Other subsystems tell us different things, right? So some subsystems say, yeah, you might actually want a mid-range style on this sub-team. Or, and this was actually the most extreme innovative subsystem we could find. And it doesn't get you all the way to the upper end, but it pushes you up there. So what this says is that we actually know what the right or what a better cognitive style should be for every sub-team on the team. So the question becomes, do we want to do random assignment of teams to, or of individuals to sub-teams, or strategic allocation, right? So taking into account what we know about their cognitive style and trying to align that to our measured cognitive style for the team. And when we do that in our computational work, we end up seeing a huge effect. So effect size of about 1 and statistically significant. We have done what I would call face validity experiments. So we've run some workshops with companies that put them through similar paces, and we see a lot of similarity to our to our computational experiments. And we're planning a more rigorous human subject study. So that's an example of the agent-based modeling work that we do in my lab. Next, I want to move on to, okay, once we have an idea for how to, or what people struggle with, how do we help them out? How do we help them be a little more efficient or be a little better at what they do? And one of the frameworks that I like to use to think about design tasks and design affordances and how we can support designers is something called the situated FBS framework. So what this is essentially a flowchart that describes design. So on the left side, we start off with requirements. On the right side, we get documentation out of it at the end of the day. In between, we go through a stage of defining functional requirements, measuring some expected behavior, figuring out some actual behavior based on the structure of the design, and then iterating on that structure. And there's a lot of really interesting stuff that happens in this central triangle. So if we go from an actual structure to the behavior expected from that structure, that is essentially the process of doing a simulation, right? So we're taking an artifact, we're figuring out how it works. We refer to that in this framework as analysis. When we compare the behavior based on the structure to our expected behavior, we're doing evaluation, right? So we're comparing outcomes to expectations. And then if we're going from expected behavior to a structure, we're doing synthesis, right? So this loop contains a lot of stuff that we do in engineering design. And I've had students who've worked on different pieces of this loop. So I'll show some examples of synthesis, specifically targeted at design for additive manufacturing. But I've also had some students who look at these outer loops. And these outer loops are reformulation steps of the problem. But I'll focus in today primarily on synthesis in the area of design for additive manufacturing. Additive manufacturing is an area where CMU is really strong. We do a lot of work in what's called process development, where we're developing new technologies like wire arc additive manufacturing or laser powder bed fusion. We also do a good amount of design for additive manufacturing. So DFAM is the process of figuring out how do we design a structure to actually be produced efficiently through 3D printing and make use of that process. And one of the things that we can do is lattice structures. So lattices are great for a variety of reasons. They absorb a lot of energy. They tend to give you very strong, lightweight structures. And we can look at uniform lattice structures, right? Just a simple grid. We can think about braided lattice structures where we're changing the thickness of that grid. But we can also think about multi-lattice structures. So multi-lattice structure is the generalization, right? What if we can use patterns flexibly to put material exactly where it belongs? And this has been a dream for quite some time. There have been people who develop these algorithms that allow us to optimize structures with respect to this lattice expectation. I have two issues with these, though. First of all, they're a little bit ugly. These are not aesthetic transitions. These are high performance transitions. And second of all, the control provided to the designer is relatively limited, right? So this is an algorithm that spits out an optimized structure, and you have very little say about what it does at the end of the day. So what we wanted to do is expose more designer control for both aesthetics and performance. And we did that using variational autoencoders, one of my favorite hammers. Happy to talk more about them later. But we trained an embedding that was based on all of the different lattice unit cells. So these are some examples of lattice unit cells that were generated by some colleagues. White shows material presence, black shows material absence. So we have some really basic gridded lattice unit cells. Then over here, these were actually topology optimized to give a variety of different behaviors and different structures. So you could imagine this one is probably going to be pretty stiff from side to side, or maybe a little more squishy from top to bottom, right? So we have lots of different properties. But if we just focus on the pixels, we just treat these as images, right? We can train an image embedding and then do interpolation within that latent space. So when we do that process and do that interpolation, what we can do is very rapidly and very easily generate structures that look like this, that have smooth transitions between different lattices. And here we only have 4 control points each. So the corners of the lattice space are defining everything that goes on in between. Everything in between is interpolated in our latent space. And this is focused at this point on aesthetics, right? We really want to have a nice smooth gradation. The next step was, okay, can we now extend this embedding to account for performance information? So we ran a computational algorithm that took all of these lattice cells and smushed them in every direction possible. And that gives us a vector of 9 numbers that describes the performance of that unit cell. So we add that onto our embedding vector. Now we have an embedding that represents both aesthetics and geometry, and performance. So now we can start to do performance-driven topology optimization in a way that we expect to be smooth and aesthetic. So we put our algorithm or put our latent space into a topology optimization algorithm. In conventional topology optimization, you would just decide whether every cell should be a 0 or a 1, right? Material absence, material presence. Here, we represent every unit cell as a latent vector. So now we're optimizing over the parameters of that latent vector. Show you a few examples. So this is a direct side-by-side example of conventional topology optimization, full cells, and our lattice-based topology optimization, where every cell is a tiny little lattice. And what's interesting here is we actually start to see some stuff that makes sense from a mechanical design perspective. So in mechanical design, especially structural design, we really like trusses. So a truss is a structure that is free to rotate at the ends. And what that means is that you're axially loading all of your structural members, which is a direction that they're really strong in, right? And if you zero into like right here, right, what we see is a really solid strip of material that's then being inserted into this, relatively smushy lattice material. So this allows it to act more like a truss and take loading in exactly the right way. So this opens up design flexibility for designers, and it's actually aligning with some of what we know from design practice in a deep way. I'm actually going to skip ahead a little bit. So we can talk about reinforcement learning if you have questions. We used reinforcement learning to do multi-fidelity optimization. Happy to come back to that. But I want to move on to some of our work that's focused on human AI collaboration. So here, we especially like to think about the space of possibilities using this 2x2 matrix. And this was developed in an engineering design context. And certainly, I'm coming at this as an engineer, so this might not cover all of the potential cases, but I think it does a good job of charting what we might care about. So on one side, we have a decision of problem-focused versus process-focused, right? A problem-focused AI tool or assistant is one that might help you find a solution, right? Sort of like the topology optimizer that we were just looking at, right? So the solution might, or this system might provide you with something that solves your problem. On the other hand, process focus means that this AI doesn't really know anything about the problem you're solving, but it knows a little bit about the process your team should follow, right? It knows when people aren't being able to speak enough. It knows when people aren't being listened to within the team. And then we can also look at reactive versus proactive. Reactive systems being ones that you treat like a tool, you hit a button, get a response. Proactive systems being ones that might shoot you an email or ask you to do something or prompt you. So I've had students, especially recently, mostly working on the proactive side of the spectrum. And today I'll talk about work by Zeta Shu and Scotty McGee, who are two of my PhD candidates in mechanical engineering. So Zeta Shu was working on a project when we first got here that focused on last mile logistics. So last mile logistics is this idea of, okay, we've got boxes in warehouses. How do we move those like 5 miles to somebody's home, right? Getting stuff to warehouses is easy, right? Getting it to the point of delivery is hard. So the context was, okay, what if we can do this with drone delivery services? So we put together teams where, you have somebody who's in a business role and is making sure that the team turns a profit. You have somebody in operations who's figuring out where to route drones. And then you have a design division that's designing drones, coming up with new drones. So this was our context for studying human AI collaboration. We've run a variety of different studies, so we covered every quadrant of this quad chart. I want to show you our AI as partner study. So the actual interface for the system is essentially a stripped down CAD environment. So this is the drone interface. We start them off with a basic quadcopter, but then they can add on airfoils to get longer distance performance. And then we have a physics-based evaluation that will return range, velocity, cost, and payload for that system. This is all open source. Believe it's on GitHub under the name Hyform, HYFORM, and I can also help you find it. The other thing I want to note is along the right-hand side, we have a chat channel. So that is the primary mode that teams use to communicate. And what that allows us to do is capture in rigorous detail all of the information that they exchanged. So we have operations as well. Looks like a map view of the city. We're figuring out which locations drones should go to. And then our business interface looks similar to what we have for operations, but they have a basic dashboard that allows them to compare different delivery plans. The beauty about developing this from the ground up is that we were also able to instrument the heck out of it. So we capture every point and click, we capture every message sent back and forth, and we capture all of the designs that are saved out of the system by individuals. And in this study, we wanted to compare purely human teams, right? So this is our human team. We have a problem manager who's in this business role. We have 2 design specialists working on drones and 2 operations specialists working on deliveries. And we want to compare this to a hybrid team that has 2 of these humans replaced with AI agents. Took us a while to publish this paper, so it got published in 2024. We started this in the pre-GPT days. So these are AI agents that were maybe not as intelligent as we would expect now. So we did a lot of work looking at prior studies and building an expert system that would emulate characteristics of the decision-making that people were doing there. So this is, I would say, maybe looks like, acts like AI agent, as opposed to the modern AI agents that we expect. Very accurate to call it an expert system. So within this context, we wanted to see how hybrid teams adapt and overcome failure differently than human teams. So halfway through the experiment, we added a shock. So that shock was, first, we're going to put hanger walls, so your drone can only be some certain size. And then second, we're going to put a no-fly zone in town. And importantly, these constraints were only represented to the human members of the team. So this was never something that we built into the expert system to even understand. So this was information that was only available to the human members. So we were creating an information asymmetry within the team. Our expectation is that human and hybrid teams would do about the same in terms of quality in the first half of the experiment. And then the second half of the experiment, all of the hybrid teams would tank, right? Because two of their members become useless. You saw the initial results, and I had a heart attack. I was like, did the manipulation just not work? Did it not go through? Like, what happened? Because this shows profit, right? We have our human teams in green, our hybrid teams in orange, and it's pretty much the same from session to session, right? We don't see that big drop that we were expecting for the hybrid teams. If anything, we might see some indication that we get some more outliers on the upper end with our hybrid teams. So what happened? First thing we started doing was looking into the communication logs, right? So what were these folks talking about? How were they communicating? How were they collaborating? And we saw some really interesting changes in the human AI communication. So we're only looking at hybrid teams. So human to human communication is shown in blue. That stays about the same from session 1 to session 2. But in session 2, there's this huge spike in the amount of human to AI communication, right? If we dig a little further, this was centralized in the operations specialist, a little preferentially. So we have some reasons to believe that they're sort of central to the team, right? They sort of play this negotiating role between business objectives and drone capabilities. So that sort of makes sense for them to be central. But really what we were seeing, I want to be careful about overclaiming because these were expert systems, right? But some like naive prompt engineering, right? So people were figuring out how to prompt around the issues that they were encountering, that they'd been told by the experimenters, in order to coax meaningful work out of their AI agent teammates. So it was great. Operations specialists were able to make this happen. We talked to them after the experiment, and they were pissed off. They were stressed out. They're like, why did you give us these terrible AI agents that we had to like drag kicking and screaming to the finish line? So I think this is an important insight that we need to consider when we design systems is where does the adaptivity fall? Where's the burden of adaptivity? Are we placing that with a human member of the system? In which case, yeah, we might need to compensate them a little more, give them some more days off, something like that. Or are we placing the adaptivity on the AI side of the system? In that case, we need a lot more development effort in most cases. So big takeaways from this experiment. We saw that our hybrid teams were about on par with people. There was this drive to communicate, to adapt, and we saw kind of the rise of an AI handler, somebody who took on the role of really negotiating with AI agents. So that's our work in this AI as partner sphere. I also want to share some of our work on AI as coach. So there's a workshop coming up in a couple of weeks called the Collaboratorium that's being held in Tepper. And I'll be sharing some more about the AI coach there. So little plug. But here we're looking at just basically, can we create a coach that emulates the characteristics of a human coach, right? The idea being, can we provide, process guidance for people, a little buddy that helps them decide what next step to take in design, and really help optimize their process. So here we have very similar team setup to our last study, except now we have a little coach hat sitting on top of the team. This can either be an AI coach or it can be a human coach. So for our human coaches, we gave them access to all of the information that made sense for them to see within the team. So they had limited chances for interaction, but they saw a lot of what was going on. So this was their interface. They got all of the essentially action trace from their teammates. They got to see the communication logs that their teammates were passing back and forth. And they were also able to chat with the experimenter if they ran into issues. But they were constrained to a set of 13 interventions. And these were exactly the same set of interventions that we gave to our AI coach. So we're trying to blind this experiment as much as possible. Our AI coach took in essentially the same information that we provided to our human coach and put out the same set of interventions. So our AI coach took in action and communication data, compared those to a prior team that had done well on the task. Remember that, we'll come back to it. And then makes decisions about action being too high, too low, communication being too high, too low, too unfocused, and then decides accordingly on one of the interventions. When we look at the final performance in terms of profit from these teams, we end up seeing that our human coach and our AI coach aren't too different. We might have a little bit of an AI advantage in the second session again, but this was not significant. So I don't want to rely on that too much. But we can break down the type of interventions that the AI coach and the human coach used. Right? We can look at the frequency of whole team interventions versus one-off interventions to individuals on the team. And what we see there is if we look at action interventions, communication interventions, and no interventions, we see some differences, looks about the same, but if we take out the no intervention cases and renormalize, it would almost exactly the same in terms of the distribution. So we're excited to see that. This difference is really interesting though. So we have human process managers, human coaches deciding not to intervene at a rate that's 2 to 3 times higher than the AI coach. So this gives us an indication of maybe one of the challenges we need to solve in AI coaching is timeliness, right? And I know there are many folks here at CMU looking at exactly that problem. But the biggest issue is that we had to compare to a prior good team solving the same task. And that has bugged me for years. So Scotty has been thinking deeply about what we can bring in from the psychology literature to help us better guide teams with less knowledge about the problem. And we've come to something called collective intelligence. So especially with Anita Woolley here at CMU, CMU has a pretty good history of collective intelligence. In broad strokes, this is like an IQ at a team level. And there are a few specific sub-factors that we know that are especially influential across cases and across environments. So social sensitivity of the individuals, the degree to which they show coordinated attention on the problem, and also equality of participation. So these are things that we can measure, track, and trace during problem solving, and nudge according to those to try to coax better behavior from the team. So here we moved on to a problem that was a little bit more qualitative and much less optimally framed. So this is probably the closest thing we have to a diagnostic problem in engineering design. So there are like 30 something papers that have used this problem. This is the standard framing. So, you're shelling peanuts. You have a target of like 100 kilograms an hour. You have basic materials. You can't plug it into a wall, so you're limited to like basic electricity. You also have a mass or a cost minimization objective. And what we were asking from these teams, this is a relatively short experiment, was a systems diagram like this. It would show what parts of the system come together in what form to do this task. And we compared AI coaching versus human coaching. So our AI coach, again, is using collective intelligence to identify how to intervene, rather than specifically referring to a good prior team. And when we look at the performance, again, in terms of profit, we see, not profit. So we had experts rate these solutions in terms of poor, good, or excellent. And we see our red teams being human coach teams and our blue teams being the AI facilitated teams. So we see a significant shift towards the upper end. This plot shows the number of interventions in the first, second, and third period of the experiment. And we see that actually drops off pretty precipitously. So we're still digging into this. We have a hope, a hunch, an indication that this is actually some learning that's going on through this coaching process, but we need to dial that in a little bit more. So when it comes to human AI teaming, the last couple of years have been really exciting because the types of AI we have access to have gotten more exciting, more capable, more human adjacent in some ways. So didn't want to focus on this in the talk, but we've done some LLM stuff. So we've looked at KAI. We've developed a prompt that can make a language model generate ideas in the same way as somebody who's cognitively adaptive or innovative. We've used language models to drive material selection. We've created language models that can serve as AI tutors as opposed to AI tutors. This actually helps make mastery in mechanics. We showed a significant increase in spring force last spring. But I mean, I don't want to preach to the choir, right? But what I do want to talk about as I close out my talk is in a future where all of this is possible, right? Where computers can do all of this and even more, what will be left for human designers? Maybe the better way to ask that question is what should be left for human designers? So who knows what PDoom is? Okay, what's your PDoom? Don't want to put you.
It's a very
Fair. So PDoom is sort of a meme that gets thrown around, but it's what is your probability that you assign to AI leading to the doom of humans, right? Downfall of humanity on Earth. So as we think about possible futures, the first one that comes to mind is, okay, what if PDoom approaches 1? That's bad. We don't want that to happen, right? I think we can all agree that we want to keep PDoom much less than 1. So this is not a preferred future. Potential future number 2, as a species, we can aggressively drive PDoom to 0 and live a pastoral future. Some nice things to like about this, but probably not the one we're most excited about. So the first thing I want to pull out is if we want a tech-enabled future, I think we need to accept a small amount of PDoom, right? We got to bite off some risk if we want value. But there are a lot of intermediate points, right? There are a lot of values that fall between 0 and 1, and a lot of different ways that those could look. So one possible future, especially when it comes to design, is maybe humans are going to end up doing the physical parts of design. So there is a lot of research focused right now on fine motor manipulation for robots. Huge open problem, right? Everyone, I think everyone, don't want to make any assumptions about ability, but most of us have, 2 multi-$10 million manipulators attached to us, right? Hands are amazingly useful. And it's possible that growth in intelligence of computational systems outpaces growth in physical abilities, and we become manufacturers, right? One possible future. We might end up doing the early stages of design. So in early front-end design, that tends to be more human-facing. In later stage design, that's where we might do some optimization or use more computation. So this is a divide that we're already starting to see some of, right? A lot more AI use in later stages of design, a lot more human involvement in early stages. Another way to think about this is, maybe in a post-scarcity future, we're just going to get to do what we like, right? I've been teaching a lot of sophomores for the last couple of years. They really like working in CAD. So maybe their preferred future as engineers is, okay, I'm going to work in CAD and do the stuff that I like. And there's a lot to like about this future, right? Valuing enjoyment in human existence. But the future that I prefer is that in design, humans are going to be there to do the most human things, right? Empathy, working with others, mentoring young engineers, helping people grow and change and learn. And I think that's really the future that I want to find, and the future that I hope we can all find together. So with that, I'd like to recognize a fantastic group of collaborators and PhD students who I've had the pleasure of working with over the years, as well as a whole slew of other collaborators who I've really been blessed to work with. So with that, thank you so much. I'd be happy to take any questions you have.